Something in the nearby universe is pulling entire galaxies across space, including our own Milky Way. Astronomers call it the Great Attractor, but what it really is remains one of the strangest mysteries in cosmology. Hidden behind the stars and dust of our galaxy, this enormous gravitational region may be reshaping the motion of everything around us. If that sounds like the kind of cosmic mystery worth exploring, make sure to like the video, subscribe to the channel, and let's step into the hidden flow of the universe. At the widest scale that astronomy can map in the nearby universe, galaxies do not lie in space as a smooth and even mist. They gather into a vast pattern of threads, knots, sheets, and open gaps. This pattern is often called the cosmic web. The word web is a simple name for something very large and very quiet. It does not mean strands like silk stretched in air. It means that matter, over immense spans of distance, settles into connected shapes. Galaxies cluster where matter is dense. They line up along long filaments where gravity has drawn material together over long stretches of cosmic time. Between these richer regions lie voids, broad areas where galaxies are fewer and matter is thinner. Across this arrangement, the universe keeps its overall order while remaining highly uneven from place to place. In this broad setting, a single galaxy is not the main feature. Even a great spiral full of stars becomes a small point within a much larger geography. Galaxy groups gather into clusters. Clusters sit along filaments. Filaments join superclusters and larger flow patterns. The result is a kind of landscape made not of soil, rock, or water, but of matter spread across expanding space. Astronomers study this landscape by measuring where galaxies appear, how far away they are, and how they move relative to the general expansion of the universe. From that work, the largest visible pattern begins to emerge as a connected structure rather than a scattered collection of islands. This large-scale order begins very early in cosmic history, after the early universe cools enough for matter to move more freely. Tiny differences in density start to matter. Regions with slightly more mass pull in more material. Regions with slightly less mass give up material more easily. Gravity acts slowly, but it acts everywhere. Over billions of years, small differences grow into larger structures. Matter streams inward toward denser regions. Filaments become more defined. Clusters become heavier and more tightly bound. Voids widen as matter drains away from them. The cosmic web is the long result of that patient reshaping. It is not a rigid frame built all at once. It is a changing pattern that grows clearer as gravity amplifies the first unevenness. Seen in very large surveys, the web has a remarkable calm. Dense clusters mark the intersections of filaments like bright cities along the meeting points of roads. The filaments themselves contain galaxies, gas, and large amounts of dark matter, the unseen mass that reveals its presence through gravity. Around them, the voids appear almost empty by comparison. Though they are not perfect nothingness, they still contain matter, only far less of it. This contrast between dense regions and thin regions is one of the key facts of the nearby universe. The universe, on the largest scales, is not chaotic. It has structure. It has shape. It has regions where gravity gathers and regions where gravity yields. The word nearby in astronomy still covers distances so large that ordinary intuition becomes useless. The nearby universe includes countless galaxies spread across millions of light years. Even within this range, the structure is already grand enough to contain enormous clusters and superclusters. Astronomers map these systems because local motions make sense only inside this wider setting. A galaxy does not move through an empty and featureless background. It moves within a landscape of surrounding mass. Any attempt to understand why a galaxy group drifts in one direction must begin with the mass distribution around it on very large scales. The broad map comes first because motion gains meaning only when placed inside structure. This is why the cosmic web matters for the mystery of large-scale attraction. Gravity does not operate only from single compact objects. It also emerges from extended regions of mass, from clusters, from chains of clusters, from walls of galaxies, and from dark matter spread across volumes too large to imagine directly. A galaxy may respond to the pull of nearby concentrations, to the absence of matter inside adjacent voids, and to the combined effect of structures spread across enormous distances. In that sense, the web is not only a picture of where galaxies are, it is also a map of where gravitational influence is stronger and where it is weaker. The web is both structure and motion made visible in slow form. When astronomers describe this large pattern, they often rely on careful distinctions. A cluster is a gravitationally bound collection of many galaxies. A filament is an elongated bridge of matter linking richer regions. A supercluster is a broader concentration that may include several clusters and filaments, though not all of it is bound together in the same simple way. A void is a region with comparatively few galaxies. These terms allow the large landscape to be described without mystery. They show that the universe can be studied as a geography of density. Once those terms are clear, the sky begins to look less like random scatter and more like terrain shaped by time. At this widest regional level, one fact stands above the rest. Matter is unevenly distributed. That unevenness is the essential background for everything that follows in the nearby universe. It explains why some regions are crowded with galaxies while others are sparse. It explains why large-scale surveys reveal patterns instead of uniform spread. It explains why gravity can create collective motion across immense distances. Without this uneven distribution, each galaxy would simply recede in the general expansion with little additional pattern to observe. With uneven distribution, the broad drift of matter becomes richer and more complex. The Great Attractor belongs first to this widest setting. Before it is anything else, it is part of a universe whose nearby matter is arranged in large connected structures. It is not understandable as an isolated marvel detached from its environment. It arises inside the cosmic web, inside a geography where mass gathers in some directions more than others. The broad outer region therefore begins not with a hidden centre, but with the visible architecture of the surrounding universe itself. In this architecture, galaxies are carried within larger arrangements, and those arrangements preserve the long history of gravitational growth. The largest map is quiet, but it is not still. It holds the record of how matter gathers, how emptiness expands, and how the nearby universe takes on shape. Across the large structure of the nearby universe, the most basic motion is not a fall inward but an opening outward. Space itself expands. This is the quiet background against which all other large motions must be understood. Galaxies that are far from one another tend, on average, to grow more distant with time. This general recession is not best imagined as galaxies flying through a fixed emptiness like sparks through air. It is more accurate to think of the distance between large regions of space increasing. The farther away a galaxy lies, the greater its average recession tends to be. This broad pattern gives the nearby universe its main rhythm. It is smooth in principle, though never perfectly smooth in practice. Astronomers describe this overall trend as cosmic expansion. It provides the baseline motion expected from the growth of the universe on large scales. If matter were spread in a perfectly even way, and if every region followed only this global expansion, then galaxies would recede in an orderly pattern set mainly by distance. A more distant galaxy would usually be moving away faster than a nearer one. In that simple picture, the map of motion would be clear and regular. Distance and recession would closely match. The nearby universe would still contain structure, but its motions would be easier to read because the background would dominate without much disturbance. Yet the real universe does not behave with such full simplicity. Matter is not evenly spread, and gravity continues to work inside the expanding background. Wherever matter gathers more strongly, the expansion is modified. A galaxy near a dense region may still take part in the general outward growth of space, but it may also gain an extra motion towards surrounding mass. In thinner regions, where matter is scarce, galaxies may drift away from the emptier area as denser structures elsewhere exert greater influence. The result is a layered pattern of movement. First, there is the broad outward trend of expansion. Then there are smaller departures from that trend, added by the uneven pull of matter. This distinction is essential. Without it, every motion might appear to point towards some hidden and dramatic cause. With it, the picture becomes calmer and more precise. Most of the recession seen across the nearby universe belongs to expansion itself. Only part of any galaxy's motion reflects the local or regional influence of gravity from nearby structures. Astronomers must therefore separate the background flow from the extra drift. They do this by measuring distance as carefully as possible and comparing that distance with the galaxy's observed recession. If the observed motion differs from what expansion alone would suggest, that difference carries meaning. It points to the influence of surrounding mass and to the uneven structure of the cosmic web. The expansion background also sets the scale of interpretation. In the very nearest regions, gravity can dominate strongly enough that some systems remain bound together rather than being carried apart by expansion. Galaxies inside a cluster, for example, may orbit within the common gravitational hold of the cluster, instead of receding from one another in the ordinary way. On somewhat larger scales, expansion becomes more apparent, though still modified by local mass concentrations. On larger scales again, the general outward pattern grows stronger and clearer. This means that motion in the nearby universe must always be read by scale. A behavior that seems unusual in one region may be normal in another. Expansion is the common background, but its visible expression changes depending on how strongly gravity shapes the local setting. The light from distant galaxies helps reveal this pattern. As space expands, the wavelength of light stretches along with it. This shifts the light toward the red end of the spectrum, a phenomenon called redshift. Redshift is one of the main tools astronomers use to estimate recession. A larger redshift usually means a greater recession, and, in many cases, a greater distance. But redshift alone does not tell the whole story, because gravity adds extra motion. Part of a galaxy's redshift may reflect more than expansion. It may include a local drift superimposed on the broader outward trend. This is why distance measurements beyond redshift itself are so important. They help identify where recession follows the average cosmic pattern and where it departs from it. Once this is understood, the nearby universe looks less like a uniformly swelling sphere and more like an expanding landscape with currents in it. The expansion acts everywhere, but not everything moves with equal simplicity. Large structures disturb the flow, dense regions slow the local expansion, redirect it, or draw matter inward relative to the background. Broad underdense regions can contribute in the opposite way by leaving galaxies less restrained nearby. So that motion appears to stream away from emptier areas toward richer ones. The cosmic web remains the setting, but now it becomes a moving setting, one in which the average outward opening of the universe coexists with quieter internal rivers of motion. This layered motion is the foundation for understanding attraction on large scales. The general expansion is not an obstacle to gravity. It is the stage on which gravity acts. Galaxies do not choose between expansion and attraction, as though one cancels the other completely. Instead, both operate together. The background pushes distances larger on average, while uneven matter creates departures from that average. These departures are often modest compared with the full recession over very large distances, yet they are rich in information. They show where mass is concentrated, where the cosmic web is shaping motion most strongly, and where the nearby universe departs from smooth simplicity. For this reason, astronomers treat the background expansion as the first motion that must be known before any secondary motion can be interpreted. It is the reference against which drift becomes visible. Without the expanding background, there would be no clear way to identify which motions are ordinary and which reveal extra pull. The mystery of large-scale attraction begins here, not with a hidden object, but with the careful subtraction of the expected cosmic flow from the actual motion observed. Only after that quiet work does the map of departures begin to appear. The outer region of the problem therefore remains broad and fundamental. The universe expands, and within that expansion, matter leaves subtle traces of unequal gravity. The background flow provides the calm surface. The deviations mark where the deeper structure presses through, within the wide pattern of the nearby universe. The next inward region is the local group, the small gravitational community that contains the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and many smaller companion galaxies. On the scale of the cosmic web, this group is modest. It is not a cluster crowded with hundreds or thousands of large galaxies. It is a quieter association bound by gravity across a few million light-years. Yet for understanding large-scale motion, this small community matters greatly, because it is the frame from which nearby cosmic movement is measured. The Milky Way is not treated as an isolated observer. It belongs to the local group, and the group itself moves through the wider universe. The local group has an internal structure of its own. The Milky Way and Andromeda are its dominant members. Each is surrounded by smaller galaxies, and together they shape the group's gravitational balance. Over long periods, their mutual attraction governs much of the local arrangement. These internal motions are real, but they are not the largest concern in this region. What matters here is the collective motion of the group as a whole, relative to the broader cosmic background. Astronomers therefore distinguish between local orbital motions inside the group and the drift of the entire group through surrounding space. The first belongs to the small-scale life of neighbouring galaxies. The second reveals how this local community sits inside the larger gravitational landscape. This collective motion is not guessed from appearance alone. It is inferred from observation with great care. One of the clearest clues comes from the cosmic microwave background, the faint afterglow of the early universe. This radiation fills the sky in all directions and provides a useful reference because it comes from a time long before galaxies took their present form. If the local group were perfectly at rest with respect to this background, the radiation would appear nearly the same in every direction, apart from very small natural variations. Instead, One side of the sky appears slightly warmer and the opposite side slightly cooler. This pattern shows that the local group is moving relative to that ancient light. The motion creates a directional imbalance, with radiation in the direction of travel shifted to slightly higher energy, and radiation in the opposite direction shifted to slightly lower energy from this effect. Astronomers estimate that the local group moves at several hundred kilometers per second relative to the cosmic microwave background. The exact value depends on the frame used and on how the motion of the Sun and the Milky Way within the local group are removed. But the essential fact remains stable. The local group is not simply at rest while the universe expands around it. It has a substantial motion of its own through nearby cosmic structure. This measured drift is one of the strongest signs that the surrounding distribution of matter is uneven enough to shape motion on very large scales. The meaning of this motion becomes clearer when the smaller layers of movement are removed one by one. The Earth moves around the Sun moves within the Milky Way moves relative to Andromeda and the other members of the local group. Once these internal motions are accounted for, a broader shared drift remains. That shared drift belongs to the local group itself. This process of correction is part of the discipline of astronomy. It turns a complicated set of overlapping motions into a cleaner picture. Only then can the larger movement of the group be understood as a response to the surrounding mass distribution of the nearby universe. The direction of this motion on the sky is also important. It does not point randomly. It points toward a region where the distribution of galaxies and mass is richer than average. Though the full picture is complicated by obscuration from the plane of the Milky Way, and by the presence of several large structures in roughly related directions. Even without naming every contributing region, the measured drift of the local group shows that the group lies in a gravitationally uneven environment. The nearby universe is not balanced around it in every direction. There is more pull along some paths than along others, and the group responds to that imbalance. This does not mean the local group is rushing through space in a violent or exceptional way. On cosmic terms, the motion is steady and ordinary, the natural result of gravity acting over immense timescales. The scale is large, but the process is calm. Gravity shapes trajectories gradually, over billions of years. Even modest imbalances in pull can produce significant motion. The local group therefore carries within its drift a long history of surrounding structure. Its present movement is not a sudden event. It is the accumulated result of the mass around it, both seen and unseen, distributed across a large part of the nearby universe. The local group also illustrates an important truth about cosmic perspective. From within the Milky Way, the sky can seem centered on local concern stars, gas clouds, nearby galaxies, and the bright band of the galactic plane. Yet when the motion of the local group is measured against the ancient radiation field of the universe, the scale of the problem changes at once. This small group of galaxies, including the one that contains the solar system, is itself in transit. It is part of a wider flow. It does not stand apart from the large architecture of matter. It is embedded within it and shaped by it. In this regional view, the local group becomes the first intimate piece of evidence that the cosmic web is not merely a static map. It is also a dynamic environment. The web has enough structure to give a measurable drift to our galactic neighborhood. The local group is small enough to feel familiar in astronomical terms, yet large enough to register the pull of structures far beyond its own boundaries. Its motion forms a bridge between the broad expansion of the universe and the more specific geography of surrounding mass. The group drifts because the universe nearby is uneven, and that unevenness leaves an imprint even on the motion of the home system, that contains the Milky Way. A galaxy in the nearby universe takes part in the general expansion of space, yet its motion is often not limited to that smooth outward pattern alone. When astronomers compare a galaxy's measured recession with the recession expected from distance, they often find a difference. That extra motion is called peculiar velocity. The word peculiar does not mean strange in a dramatic sense. It simply means motion relative to the average cosmic expansion. A peculiar velocity is the part of a galaxy's movement that belongs to local and regional gravity, rather than to the general widening of the universe. This idea is one of the most useful tools for reading the hidden distribution of mass. The concept begins with a simple comparison. If a galaxy lies at a certain distance, the expanding universe suggests an average recession for that distance. If the observed motion is slightly faster or slightly slower than expected, then some additional influence is present. That influence is usually gravity from nearby or larger structures. A galaxy may be moving toward a dense region, away from a thin region, or as part of a wider flow shared by many galaxies in the same area. The difference between the expected recession and the observed motion becomes a clue. It turns motion into evidence. It allows astronomers to look beyond the visible placement of galaxies and trace the underlying pull acting on them. This makes peculiar velocity signals especially valuable. Light reveals where galaxies are, but motion reveals what the surrounding mass is doing. A galaxy can sit in a region that looks modest in visible light and still show a clear drift caused by mass distributed nearby or beyond direct view. In this way, peculiar velocity becomes a bridge between what the sky shows and what gravity implies. It is not a separate kind of motion from ordinary motion. It is the measured remainder after the broad expansion is accounted for. Yet this remainder often carries the deeper message. To detect such signals, astronomers must know more than redshift alone. Redshift shows how much a galaxy's light has shifted toward longer wavelengths, and that usually indicates recession, but redshift combines more than one effect. It includes the large background expansion, and it also includes any extra motion toward or away from the observer. To isolate the extra part, astronomers need an independent estimate of distance. This is a difficult task because cosmic distances are not measured with a ruler. They are inferred from reliable indicators such as certain kinds of stars, certain kinds of supernovae, or patterns in galaxies whose true scale or brightness can be estimated. Once distance is established, the expected expansion can be compared with the actual recession. The remaining difference is the signal of peculiar motion. These signals are often not large compared with the full recession of very distant galaxies, but in the nearby universe they matter greatly. On these scales, the extra drift can represent a meaningful fraction of the total observed motion. A galaxy may appear to recede more slowly than expected because it is moving toward a mass concentration. Another may seem to recede more quickly because it is being drawn away from a relatively emptier region or carried along by a larger flow. A set of galaxies in the same volume may show a common directional drift, revealing that the entire region is moving together through the surrounding cosmic landscape. When many such measurements are gathered, the nearby universe begins to show patterns not only of position, but of streamlike motion. This is why peculiar velocity studies require both patience and caution. The signals are subtle. Distance measurements carry uncertainties. Local motions within groups and clusters can complicate the picture. A single galaxy may have its own orbital motion within a bound system, and that internal motion may partly mask the larger regional drift. For this reason, Astronomers often look for collective behavior across many galaxies rather than trusting one isolated case. When a broad set of galaxies shows a consistent excess motion in a common direction, confidence grows that a real large-scale flow is being seen. The power of the method lies not in a dramatic individual object, but in the calm agreement of many measurements. Peculiar velocity also changes the way recession maps are understood. A simple redshift survey can suggest where galaxies lie and how fast they seem to move away. But without correcting for peculiar motion, dense regions can appear stretched or distorted in redshift space. This happens because galaxies inside a cluster move in different directions around the cluster center while also taking part in cosmic expansion. Their internal motions alter their apparent placement along the line of sight. In broader regions, shared drift can shift whole structures away from where a purely expanding model would place them. Peculiar velocity therefore matters not only as evidence of hidden gravity, but also as a correction needed for a more faithful map of nearby cosmic structure. The idea carries an important physical meaning. Gravity does not need to announce itself through bright light alone. It can be inferred from how galaxies depart from the average flow. If enough galaxies in one part of the sky share an extra motion, then the mass distribution in or around that region is not balanced. Something is shaping the stream. That shaping may come from a cluster, a chain of clusters, a filament, or a wider region of excess mass. It may also reflect the comparative emptiness of another direction. Since motion responds to the full landscape of density contrasts rather than to one object in isolation, peculiar velocity signals therefore do not point merely to one source. They describe a field of influence. For the nearby universe, these signals are among the clearest signs that cosmic structure is active in a dynamic sense. Galaxies are not simply pinned in place within a grand design. They move within it, and their departures from the smooth expansion record how gravity continues to organize the landscape. In this region of the story, peculiar velocity is the quiet fingerprint of uneven mass. It is how the nearby universe reveals its hidden slopes without direct display. A difference between expected recession and actual motion may seem small, yet it carries the weight of large structures, dark matter, and long accumulation through cosmic time. By reading these differences carefully, astronomers find that the surrounding universe is not only expanding, it is also flowing. Once the broad pattern of extra motion is measured across many galaxies, astronomers begin to describe the nearby universe in a new way. The map is no longer only a chart of where galaxies sit or how fast they recede. It becomes a map of flow. In such a map, galaxies can be treated as if they move along gentle paths through a gravitational landscape. The image is only a guide, but it is a useful one. Matter does not move like water on the surface of Earth, yet the comparison helps clarify what the measurements reveal. Just as rain falling over land follows slopes and gathers into streams, galaxies in the nearby universe can show a collective drift along preferred routes set by uneven mass. These routes do not appear at a glance in ordinary images of the sky. They emerge when the field of motion is reconstructed from many peculiar velocities. In this setting, astronomers use the idea of a basin of attraction. A basin of attraction is a region of space within which galaxy flows tend to converge toward the same general gravitational low point. The phrase low point is another image borrowed from a landscape. It does not mean a hole in space or a literal cavity. It means a place in the distribution of mass toward which surrounding motions are directed. A basin is therefore not defined only by visible borders of light. It is defined by motion. Galaxies that share a common inward drift belong. In this sense, to the same large drainage region of the cosmic flow. This way of thinking changes the meaning of a boundary. In an ordinary star map, a boundary may separate one constellation from another by human agreement. In a cluster map, a boundary may be drawn where galaxy density falls away. In a flow map, the boundary is found where motion divides. On one side of that dividing surface, galaxies tend to drift toward one attractor. On the other side, they drift toward another. The line or surface separating those outcomes is sometimes compared with a watershed. On Earth, a watershed divides rain that runs into different river systems. In the nearby universe, a flow boundary divides galaxies that belong to different large-scale basins of attraction. This is not a hard wall, it is a transition in the direction of motion. The value of this picture lies in its calm honesty. It does not require the nearby universe to be organized around one single dominant object at every scale. Instead, it allows different regions to drain toward different centers of influence. Gravity becomes something that shapes territory. Some areas feed one flow, other areas feed another. Dense structures act like valleys in the gravitational landscape, while thinner regions stand more like higher ground from which matter tends to stream away towards stronger pull elsewhere. In this framework, a void matters not because it pushes in any direct mechanical sense, but because the absence of nearby competing mass leaves surrounding matter more responsive to denser regions beyond. The pattern of flow therefore reflects both the presence of excess mass and the relative emptiness around it. To reconstruct such basins, astronomers begin with the measured peculiar velocities of galaxies and infer the underlying velocity field, meaning the pattern of directions and magnitudes of motion across a region. Since not every galaxy can be measured with equal precision, the map must be built statistically and smoothed carefully. Individual motions can be noisy. Distances carry uncertainties. Local orbital movement inside groups can blur the larger trend. But when enough measurements are combined, a broad structure appears. Streamlines can then be drawn through the reconstructed field. A streamline is a line that follows the direction of the flow at each point. By tracing many such lines, astronomers can see where motions gather and where they separate. The map begins to resemble a terrain of invisible slopes. This does not mean galaxies are sliding freely as though in a fluid. The universe is not a liquid medium in the ordinary sense. Each galaxy remains an individual system following gravity through expanding space. The fluid image is a mathematical and visual aid. It allows many discrete motions to be described together as a smooth pattern when viewed on very large scales. In that large-scale view, the metaphor becomes powerful. It reveals that the nearby universe has coherence. Its motions are not random scattered arrows. They organize into convergences, divergences, and dividing surfaces. A basin of attraction is the name for one of these coherent domains. The idea is especially important because visible structure alone can sometimes mislead. Two rich clusters may seem equally prominent in a survey image, yet the surrounding flow may show that one governs a wider basin than the other. A chain of filaments may contain less brilliant light than a compact cluster, but still participate in guiding large-scale motion toward a common region. The true influence of a structure must therefore be judged not only by brightness or local crowding, but by the pattern of flow around it. In this sense, motion helps define the large-scale architecture more deeply than appearance alone. A basin of attraction also does not have to be static in a simple sense. The nearby universe continues to evolve, though very slowly on human timescales. Matter keeps gathering, structures keep interacting, yet on the scales relevant to present observations, a basin can still be treated as a meaningful current arrangement of shared drift. It marks a region where the collective motion of galaxies reveals a common gravitational destination. This gives astronomers a way to describe supercluster scale organization without demanding that every part of such a region be tightly bound in the same way. What matters most is not whether every galaxy is locked into a permanent structure, but whether the present flow lines show a common tendency. By this stage of the inward path, the nearby universe can be seen as a landscape of cosmic drainage. Expansion still provides the broad background, and peculiar velocities still reveal departures from that background. But now those departures acquire shape. They gather into basins, they divide at watersheds. They stream toward regions of greater influence. The map becomes quieter and more intelligible. Instead of one isolated mystery, there is a patterned field of motion. Galaxies drift as part of larger territories of pull, and those territories can be traced through the language of flow. A basin of attraction is therefore not merely a label. It is a way of seeing the nearby universe as a connected gravitational terrain, with broad regions defined by where their galaxies tend to go. The next inward region is not defined merely by where galaxies appear close together on the sky. It is defined by how large numbers of galaxies move as part of a shared flow within this view. The Milky Way and the local group belong to a much broader domain that has been described as Laniakea. The name comes from Hawaiian and carries the sense of an immense heaven. In astronomy, it is used for a supercluster scale region identified through galaxy motions rather than by brightness alone. Laniakea is not simply a heap of clusters placed near one another by chance. It is a flow-defined territory within the nearby universe, a basin in which many galaxy paths trend toward a common inner region. This idea matters because the word supercluster can suggest a clean and solid object, as though it were a larger version of a bound star cluster. The reality is quieter and less rigid. A supercluster is often a broad concentration of clusters, groups, filaments, and diffuse matter that shares a larger setting, but not every part of it is tightly bound in the same way. Laniakea is especially important because its definition comes from the motion field. Astronomers reconstruct the peculiar velocities of many galaxies and then trace the streamlines of that motion. By doing so, they identify a domain inside which the flow tends to drain inward toward the same broad basin. The result is not only a picture of matter distribution, it is a map of belonging through motion. In this framework, the Milky Way is not placed at the center of anything. It sits within one outer portion of a vast gravitational territory. The local group belongs to a filamentary environment that connects with other groups and clusters. One of the most familiar nearby landmarks in this wider setting is the Virgo cluster, a rich concentration of galaxies that has long played an important role in describing our cosmic neighborhood. The local group lies on the outskirts of the larger Virgo region, and is often treated as part of the Virgo supercluster in older language. The concept of Laniakea grows from a more dynamical understanding. It broadens the view from a simple nearby concentration to an extended basin defined by shared inward flow. This makes Laniakea less like a single luminous object and more like a continent shaped by invisible slopes. Its extent reaches across hundreds of millions of light years. Within that expanse are multiple clusters, galaxy groups, filaments, and the dark matter that helps govern their motion. Some regions are richer in galaxies, some are thinner, and some act mainly as passageways along which matter drifts. What unites them in the Laniakea picture is not uniform density or uniform appearance, it is the way their motions, when smoothed and reconstructed on large scales, indicate participation in the same drainage basin of the nearby cosmic web. The boundary of Laniakea is therefore not drawn in the ordinary way by counting visible galaxies until they grow sparse. It is drawn by a watershed in the flow field. On one side of that dividing surface, galaxies tend to stream inward within the Laniakea basin. On the other side, they belong to neighbouring basins with different destinations. This is one of the most elegant features of the concept. It allows astronomers to define a supercluster not just by shape or brightness, but by collective behaviour. The boundary is a dynamical boundary. It marks where the preferred direction of motion changes. Within this large territory, the local group follows a path that is only one part of the wider pattern. It shares the broad drift of the basin while retaining its own internal structure and local gravitational ties. This dual condition is common in the universe. A small system can remain bound within itself and yet still participate in a larger regional flow. The Milky Way orbits within the local group environment. The local group exists within the broader Laniakea basin. The basin itself lies within the larger architecture of the cosmic web. Each scale is real, and each scale adds its own level of motion and structure. The usefulness of Laniakea lies partly in the discipline it brings to cosmic perspective. It reminds astronomy that large structures are not always best described by the eye alone. A region can seem prominent in a galaxy map yet have a more limited dynamical reach. Another region may appear less dramatic in visible terms while still guiding flow across a broad area. By reconstructing motion, astronomers gain a physical picture of the neighbourhood around the Milky Way. Laniakea becomes the name for that motion-based neighbourhood, a large home basin in which the local group takes part. There is also an important note of caution in the concept. Laniakea is a model built from the best available reconstructions of galaxy motions, and those reconstructions depend on distance measurements, smoothing methods, and incomplete observational coverage in some parts of the sky. The Milky Way itself obscures certain directions, and peculiar velocity data are never perfectly complete. For this reason, Laniakea should be understood as a scientific description of a broad flow domain, not as a sharply edged and final object in the simple everyday sense. Observations indicate that such a basin is meaningful. It remains uncertain in some details exactly where every boundary lies, and how future refinements may redraw parts of the map. Even with that caution, the concept remains powerful. It gives the Milky Way a place in the nearby universe that is larger than the local group but still more specific than the full cosmic web. It says that the home galaxy is part of an immense shared basin of motion. It says that surrounding galaxies, clusters, and filaments are not merely neighbours in position, but companions in flow. It says that the nearby universe can be organised into gravitational territories whose identities are revealed through drift. Laniakea is one such territory, and for the Milky Way it serves as the regional home. In this inward step, the cosmic web becomes more personal without becoming small. The outer map of structure, the background expansion, the measured drift of the local group, and the idea of basins of attraction now gather into one named domain. Laniakea is that domain for our region. It is a supercluster scale basin defined by the shared movement of galaxies through a common gravitational landscape. The local group does not stand alone inside the nearby universe. It belongs to this larger flow-defined home, surrounded by connected structure and carried within an immense but intelligible terrain of motion. Within the broad basin that includes the Milky Way and the local group, the pattern of motion does not remain equally diffuse everywhere. As the reconstructed flow lines are followed inward across larger regions, they begin to show a clearer tendency. Many nearby galaxies and groups do not drift in random directions. Their motions, after the general expansion is accounted for, reveal a common inward bias across a substantial part of the local cosmic landscape. This is the setting in which astronomers speak of the Great Attractor. At this stage, the name refers less to a visible object than to a direction of convergence in the flow of galaxies, a region toward which many motions appear to lead. The term attractor is useful, but must be handled calmly. It does not mean a giant hook pulling galaxies through empty space in a sudden or violent way. It means a region of stronger effective gravitational influence within the surrounding large-scale terrain. When many flow lines bend in roughly the same broad direction, and when the peculiar velocities of many galaxies show that they share a common drift, the motion field suggests that the nearby universe contains a deeper inward slope there than elsewhere. The Great Attractor is the historical name given to that broad inward tendency. It emerges not first from appearance, but from motion. This is why the Great Attractor enters the story only after the broader structure has been laid out. The cosmic web provides the setting, expansion provides the background motion. The local group shows that even the Milky Way's neighbourhood has a measurable drift. Peculiar velocities reveal departures from the smooth expansion. Basins of attraction show how those departures can gather into coherent domains. Laniakea gives our region a large dynamical home. Once all of that is in place, the inward streams can be traced further toward a more concentrated region of convergence. In that sense, the Great Attractor is not a beginning. It is a deeper part of an already flowing landscape. When astronomers map these motions, they often find that galaxies in a broad part of the nearby universe appear to share an extra velocity component toward one general area of the sky. The evidence comes from many systems rather than from one remarkable object. Groups drift, clusters drift, filaments show coordinated motion. The cumulative pattern suggests that matter is organized so that the surrounding region channels motion inward. This does not mean every galaxy points perfectly toward one exact spot. The flow field is more complex than that. Local conditions alter individual paths. Smaller structures add their own influence. Yet the broader tendency remains visible. A regional current is present, and it has enough coherence to be named. This is one reason the Great Attractor becomes such a compelling idea in astronomy. It offers a way to describe the fact that many galaxies, including the local group, seem to take part in a shared inward drift across an immense volume of space. The label gathers many measurements under one simple phrase. It marks a region where the nearby cosmic landscape deepens gravitationally. It tells astronomers that the distribution of mass in that direction is rich enough, extended enough, and influential enough to guide motion on scales far larger than one cluster alone. The phrase does not solve the problem. It names the pattern that must be explained. At this regional level, the Great Attractor is better imagined as a convergence zone than as a small compact body. The flow lines of galaxies do not behave as though every path aims at a single narrow target. Instead, they suggest that a large region of excess mass shapes the motion field. The distinction matters. A convergent zone can include clusters, filaments, and diffuse concentrations of dark matter spread across a wide volume. The galaxies responding to it need not be falling toward one isolated center in the ordinary sense. They are moving within a broad gravitational terrain whose deepest accessible slope lies in that general inward direction. This picture is quieter and more physically faithful than the image of a hidden monster at the edge of the map. The Great Attractor also becomes important because the local group's motion relative to the cosmic microwave background points in approximately the same large-scale direction as the broader regional drift inferred from galaxy surveys. This agreement does not produce a perfect one-to-one map, but it strengthens the idea that the Milky Way's neighborhood is part of a larger current rather than a local accident. The local group is carried along with many other systems inside a regional flow. Its motion is therefore not merely a private history of nearby companions. It is one strand in a much wider pattern of inward movement. A useful way to picture this region is to imagine the surrounding web as a broad landscape of ridges and valleys, with the galaxy flows following the gentlest route downward through connected terrain. Some paths are broad and slow, some bend around intermediate structures, some join together gradually. Over large distances, however, many of them lead toward the same deeper part of the map. This is the level at which the Great Attractor is first recognizable, not as a detailed structure, not as a resolved cluster, not as a brightly outlined object. It is first recognizable as the destination implied by the inward pattern itself. That pattern gives the nearby universe a sense of direction. Without it, the motion field would seem distributed among many unrelated influences with no single regional emphasis. With it, the local cosmic environment becomes more intelligible. One can say that a broad portion of the nearby universe drains toward this convergence region. One can say that the Milky Way belongs to a larger motion system whose inward trend points there. One can say that the Great Attractor is not merely a famous phrase from astronomy, but a meaningful description of a real large-scale flow. It names the place in the regional motion map where the gravitational landscape appears to deepen most strongly for a large surrounding domain. At the same time, the name preserves a degree of caution. It does not pretend that every detail is already visible. It does not assume that the full distribution of mass in that inward region is simple. It marks a dynamical fact before it provides a fully resolved inventory. Observations indicate that galaxies across a large area share motion toward this sector of the nearby universe. That is the firm basis of the idea. The Great Attractor, at this stage of the inward path, is therefore best understood as the broad target of converging galaxy flows within our regional basin. It is a gravitational destination written first in motion, a deeper inward region of the local cosmic web toward which many surrounding paths quietly turn. As the inward path approaches the region associated with the Great Attractor, observation meets a serious difficulty that belongs not to the distant universe, but to the Milky Way itself. The galaxy that contains the solar system spreads a broad band of stars, gas, and dust across the sky. This band is the galactic plane, the flattened central region of the Milky Way seen from within. Because the solar system lies inside the galactic disk, the view outward through that disk is crowded and obscured. Countless foreground stars fill the line of sight. Clouds of interstellar dust absorb and scatter visible light. In some directions, this foreground screen makes the more distant universe difficult to see. The result is a region long known as the Zone of Avoidance. The name is descriptive rather than dramatic. It does not mean that galaxies avoid this region in any physical sense. It means that astronomers once avoided it in surveys because observations there were incomplete and unreliable compared with clearer parts of the sky. Behind the Milky Way's bright and dusty foreground, distant galaxies remain present, but many are hidden from ordinary optical view, where a clear extragalactic survey might reveal broad patterns of clusters and filaments. The Zone of Avoidance interrupts the map. It creates a band of uncertainty across the sky, a place where the large-scale structure of the nearby universe is harder to trace directly. This difficulty matters deeply for the Great Attractor, because the broad direction of converging galaxy flows points toward a sector of the sky strongly affected by this obscuration. In clearer regions, astronomers can build a survey of galaxies and clusters with relative confidence. They can compare positions, redshifts, densities, and large-scale patterns. In the obscured zone, much of that direct clarity is lost. The mass that influences galaxy motions may still be there, and the galaxies tracing that mass may still shine, but their light must cross a thick foreground of dust and a dense field of Milky Way stars before reaching Earth. Much of it is dimmed, blended, or blocked along the way. Dust is one of the main reasons for this hiddenness. Interstellar dust grains in the Milky Way are tiny, but over long sight lines through the galactic plane, they become collectively powerful. They absorb and redden visible light from background galaxies. A galaxy behind a dusty foreground can appear much fainter than it truly is, or it can vanish from an optical survey altogether. At the same time, the stellar crowding of the Milky Way makes identification difficult. In crowded regions, distant galaxies can be masked by nearby stars or mistaken for other sources. Even when the dust is not total, the confusion from the foreground can be enough to weaken the survey. The effect is geographical in the sky. Away from the galactic plane, astronomers can look outward into the nearby universe with much greater ease. Toward the plane, visibility drops. The boundary is not perfectly sharp, because dust and stellar density vary with direction, but the general principle is steady. The Milky Way creates a belt of incomplete vision around the sky. This is why the Great Attractor remains historically mysterious even after galaxy motions suggest a strong concentration of influence in that direction. The flow can be inferred more readily than the full structure can be seen. Motion points inward, but direct optical mapping becomes harder precisely where the map matters most. Astronomy answers this difficulty not by giving up, but by changing wavelength and method. Although visible light is strongly hindered by dust, some longer wavelengths pass through the obscuring foreground more effectively. Infrared observations can reveal galaxies whose light is partly hidden in optical surveys. Radio observations, especially those that trace neutral hydrogen in galaxies, can also detect systems behind the dusty screen. X-ray observations may reveal hot gas in galaxy clusters if the foreground does not fully prevent detection. Each method has its own limitations, yet together they weaken the barrier imposed by the Milky Way. The zone of avoidance remains difficult, but it is no longer an absolute blank. Even so, the problem is not solved completely by changing instruments. Infrared surveys still contend with overwhelming foreground stars. Radio surveys do not detect every type of galaxy equally well. Some structures remain harder to define because observational selection changes across the sky. The zone of avoidance is therefore not simply a curtain that can be lifted once and for all. It is a region where astronomers must combine techniques, compare data sets, and reconstruct the hidden extragalactic landscape with care. This adds uncertainty to any attempt to describe the mass distribution lying behind the galactic plane. Observations indicate that major structures exist there. It remains uncertain in some details exactly how all the hidden components connect across the obscured region. This obscuration also teaches a broader lesson about astronomy. The universe does not present itself from a neutral viewpoint. Every observation begins from a particular place, and for the Milky Way that place is inside a dusty disk. The home galaxy is both a platform for observing the cosmos and an obstacle in the line of sight. The same stars and clouds that make the Milky Way luminous and beautiful also interfere with the outward map of the nearby universe. The Great Attractor story therefore includes not only distant structures and galaxy flows, but also the local fact that the observer looks through a crowded galactic foreground. Because of this, the zone of avoidance becomes part of the scientific meaning of the Great Attractor rather than a mere inconvenience. The mystery grows in part from incomplete direct visibility. If the relevant region lay in a clearer part of the sky, its structure might have been recognized more quickly and described with less uncertainty. Instead, the broad inward flow points toward an area where ordinary optical surveys once left major gaps. This allowed the idea of an unseen concentration of mass to gain force. The hiddenness was not imaginary. It was built into the observational situation from the start. In this region of the script, the inward path therefore pauses within the Milky Way's own screen. The flow of galaxies has led toward a sector of importance, but the galactic plane complicates the view. The zone of avoidance marks the place where the nearby cosmic landscape is partly concealed by foreground stars and dust. It is a band of obscured extragalactic vision, not an absence of structure. Behind it, the web continues. Behind it, galaxies and mass remain present. Yet from Earth, within the Milky Way, they are harder to map directly. The great inward convergence is thus approached through partial concealment, where observation becomes a matter of persistence, alternate wavelengths, and careful reconstruction rather than simple sight. Once the obscuring foreground of the Milky Way is recognized, the inward view toward the Great Attractor region becomes less like a single march toward one hidden center, and more like the sorting of layers along the line of sight in that direction. Not every important structure lies at the same depth. Some major concentrations of galaxies stand nearer than the deepest convergence region, and therefore act as foreground features in the broader gravitational landscape. Among the important of these are the great systems associated with Hydra and Centaurus. They belong firmly within the story of attraction, yet they are best understood here as prominent nearer concentrations that shape the observed flow before the inward path reaches the densest hidden sector, farther along the same general region of sky. A galaxy cluster is a large gravitationally bound collection of galaxies, hot gas, and dark matter. In visible light, the galaxies are the most obvious members. In X-ray observations, the hot gas between them can also stand out, glowing because it has been heated to extreme temperatures within the cluster's gravitational well. The dark matter remains unseen directly, but its gravity provides much of the mass that holds the system together. Hydra and Centaurus are both rich enough to matter strongly on regional scales. They are not minor knots in the web. They are heavy concentrations embedded in a wider arrangement of groups, filaments, and surrounding matter. The Hydra cluster lies in one part of this broad foreground region, and the Centaurus cluster in another, both occupying the same general sector of the nearby universe that becomes important in studies of large-scale flows. When astronomers map galaxies in that direction, these clusters stand out as substantial concentrations. Their galaxies are numerous, their gravitational wells are deep, their surrounding environments connect with larger structures rather than ending abruptly at the cluster edge. For this reason, early efforts to explain the unusual motions of nearby galaxies naturally paid close attention to them. A rich cluster along the relevant line of sight is an obvious candidate for regional influence. Centaurus has often been especially prominent in this history because it is both relatively nearby in cosmic terms and dynamically impressive. It appears as a major node in the local large-scale structure, a place where galaxies gather densely and where surrounding matter seems organized into connected forms. Hydra, too, contributes to the sense that this region of sky contains more mass than a casual sky map might suggest. Together, they help define what has often been called the Hydra Centaurus region, a broad foreground concentration that occupies an important place in the gravitational geography of our neighbourhood. The word foreground does not imply insignificance. In ordinary vision, a foreground object may dominate the scene. The same is true here. These clusters are called foreground because they lie in front of deeper structures along the path of inquiry. Not because they are weak or trivial. Their gravity shapes the motions of nearby groups and galaxies. Their presence influences how the line of sight is interpreted. They are part of the reason the Great Attractor problem becomes layered rather than simple. When many galaxies drift in a broadly similar direction, one must ask how much of that motion is due to the nearer concentrations already visible, and how much belongs to mass distributed farther inward behind them. This difficulty is scientific rather than dramatic. Along any busy line of sight in the cosmic web, several structures can contribute to the overall field of gravity. A rich cluster may pull strongly on its local environment, while also sitting within a larger flow guided by broader mass concentrations. A galaxy group observed from Earth may show a peculiar velocity that reflects the sum of several influences rather than one source alone. Hydra and Centaurus therefore matter not only as isolated objects but as components in a nested landscape of attraction. They are nearer slopes within a deeper terrain. The surrounding structures of these clusters strengthen this effect. Clusters do not usually float alone in empty space. They sit in filaments and walls, connected to neighbouring systems by bridges of galaxies and dark matter. In the Hydra and Centaurus foreground, these connections help turn the region into an extended concentration rather than a collection of separate islands. The eye may first notice the clusters themselves, but the larger gravitational influence belongs to the whole structured environment around them. Flow is guided not only by the densest nodes but also by the connected matter between them. This is one reason the Hydra Centaurus region once appeared to many astronomers as a likely answer, or at least a substantial part of the answer, to the problem of large-scale peculiar motion. A major concentration in the right broad direction provides a plausible explanation for why the local group and many neighbouring systems drift as they do. Yet as surveys improved, the picture grew more careful. The observed motions suggested that Hydra and Centaurus are important, but perhaps not sufficient on their own to account for the full scale of convergence inferred across the surrounding region. Their role remains real, though it must be interpreted as part of a layered and connected mass distribution, rather than a complete explanation by themselves. This makes the foreground region scientifically valuable. It teaches that attraction on supercluster scales is rarely the work of one bright object acting alone. Instead, large-scale flow emerges from the combined pull of clusters, filaments, groups, and dark matter arranged across a considerable volume. Hydra and Centaurus reveal this clearly. They are visible enough to anchor the map, massive enough to influence motion, and connected enough to show that the nearby cosmic web is organized in extended patterns. They also remind astronomy that the first prominent structure encountered along a line of sight may be important without being final. In this inward step, the ocean field becomes more concrete. The broad pull associated with the Great Attractor direction is no longer only an abstract convergence of streamlines. It now passes through recognizable foreground structures whose mass can be studied directly. Hydra and Centaurus stand as major concentrations along this route, helping define the nearer architecture of the region. They gather galaxies, hot gas, and dark matter into deep wells inside a connected larger environment. Their gravity contributes to the observed drift of surrounding systems, and their visibility makes them central to the interpretation of large-scale flow. The nearer layers of attraction are already rich with real structures, and Hydra with Centaurus form foreground landmarks within this inward sector of the nearby universe. Deeper within the direction long associated with the Great Attractor, one structure stands out with unusual importance. This is the Norma cluster, also known as Abel 3627. In the scientific effort to understand the region of strongest apparent convergence, Norma comes into view as one of the richest and most massive nearby galaxy clusters in that sector of the sky. It lies close to the plane of the Milky Way, where foreground stars and dust make observation difficult, and for that very reason it remained less clearly recognized for a long time than some clusters in less obscured parts of the sky. Once surveys improved across the Zone of Avoidance, Norma emerged not as a minor detail, but as a central landmark in the hidden heart of this inward region. A rich galaxy cluster is more than a gathering of bright galaxies. It is a deep gravitational system containing many galaxies, a great reservoir of very hot gas between them, and a much larger share of dark matter than visible light alone would suggest. Norma shows all the signs of such a system. Its galaxy population is abundant. Its central concentration is strong. Its hot intracluster gas shines in X-rays, revealing a deep well of gravity capable of heating diffuse gas to extreme temperatures. The cluster is therefore not only visually populous, it is physically massive in a broader sense that includes matter not directly seen. The importance of Norma arises from both location and scale. It sits in the broad direction toward which many peculiar velocity studies point when they trace regional convergence in the nearby universe. This makes it a natural candidate for a central role in the Great Attractor picture. A massive cluster placed near the deepest part of the observed inward flow is exactly the kind of structure astronomers would expect to matter strongly. As more data became available, Norma increasingly appeared not merely as another cluster in a busy region, but as a dense node near the core of the hidden concentration that earlier work had inferred more from motion than from direct sight. Seen in this way, Norma becomes a place where several strands of evidence meet. Galaxy counts show a rich system. X-ray observations reveal hot gas bound in a substantial gravitational field. The location agrees broadly with the direction of the large-scale drift seen in nearby galaxy motions. The Milky Way's foreground obscuration explains why such a major structure could remain underappreciated for so long in optical surveys. The cluster therefore has a special scientific weight. It does not enter the story as a speculative invention. It enters as a real and measurable concentration whose properties fit the long search for a major mass excess in this hidden sector. The cluster itself is a crowded environment. Galaxies move within its common gravity at high speeds. Giant elliptical galaxies occupy the densest parts. Other galaxies show the signs of life in a tightly packed region, where close encounters, tidal influence, and the cluster environment affect their evolution over long timescales. Between them lies thin gas heated to great temperatures by the depth of the cluster potential. Though nearly empty by ordinary standards, this gas contains a large amount of ordinary matter when considered over the full cluster volume. Around and through all of it extends the dark matter component, which dominates the total mass budget. In that sense, Norma is not simply a cloud of galaxies. It is an entire gravitational ecosystem compressed into one deep node. Its position near the galactic plane adds to both its difficulty and its significance, because the Milky Way blocks and confuses direct optical views. The full prominence of Norma is not obvious to casual inspection of the sky. This means that the cluster represents a triumph of careful astronomical reconstruction. It is revealed through multi-wavelength surveys, redshift work, X-ray study, and the patient comparison of galaxy distributions across obscured territory. The fact that such a substantial cluster lies in a region once poorly mapped strengthens the historical mystery of the Great Attractor. Part of what seemed hidden truly was hidden, not because the structure was absent, but because the line of sight from Earth was obstructed. Norma is often described as lying near the dynamical center of the Great Attractor region, and this description captures its role well so long as it is handled with precision. A dynamical center is not necessarily a single perfect point toward which every motion in a large surrounding region converges exactly. It is a central concentration within the broad flow landscape, a place where the density of matter and the pattern of attraction become especially strong. Norma fits that role better than most visible candidates in the area because it combines great mass, a strategically important location, and a setting that aligns with the broader inward pattern inferred from galaxy motions. Yet scientific caution remains necessary. Observations indicate that Norma is a major component of the Great Attractor region. It remains uncertain whether the cluster alone can account for the full amplitude of the observed large-scale flows in its wider surroundings. This uncertainty does not diminish its importance. It simply reflects the fact that supercluster-scale attraction is rarely the work of one object by itself. Even a very massive cluster exists inside a larger mass distribution. Norma can sit at the heart of the hidden convergence region while still being part of a broader gravitational environment. In that sense, the cluster is central without needing to be the whole story in isolation. What makes Norma especially persuasive is that it gives the Great Attractor problem a concrete interior presence. Earlier, the inward pull appears mainly as a motion pattern, a broad destination traced by galaxy velocities. With Norma, the hidden core becomes more tangible. There is a real, dense, massive cluster in the right place, embedded in the right direction, capable of exerting strong influence on its surroundings. The mystery does not disappear, but it becomes less abstract. The Great Attractor is no longer only a name for unseen convergence. It has, within this inward region, a crowded and measurable cluster at its heart. In this section, the path inward settles on a deep node of mass inside the obscured sky. Norma stands as one of the clearest central structures associated with the Great Attractor region, rich in galaxies, hot gas, and dark matter, and difficult to observe only because the Milky Way lies across the view. Its presence helps explain why the local cosmic flow points so insistently toward this hidden sector. Its mass gives substance to the idea of a gravitational center within the broader basin. In the quiet geography of nearby cosmic motion, Norma is one of the most substantial landmarks near the inward heart of the attraction. At the inward level reached here, the Great Attractor region becomes less like a single hidden object and more like an organized piece of the cosmic web. The Norma cluster remains central, but it does not sit alone in empty surroundings. It lies inside a larger arrangement of connected structures made of galaxy walls, filaments, groups, and diffuse matter. A wall in this context is a broad, sheet-like concentration of galaxies stretched across a large region of space. A filament is a narrower, elongated bridge of matter linking denser nodes. These terms matter because they describe how mass is actually arranged on large scales. The Great Attractor region is not best understood as one compact body. It is better understood as a network whose denser knots are joined by extended structures that help guide galaxy motions. The first important idea in this region is connection, A rich cluster such as Norma gathers much attention because it is bright in galaxies, deep in gravity, and comparatively easy to identify once observations penetrate the zone of avoidance. But the full gravitational setting extends beyond the cluster core. Galaxies continue outward along preferred directions rather than ending in a neat circular border. Their distribution suggests that the cluster sits at the crossing of larger structures. This is a common feature of the cosmic web. Dense clusters tend to form where filaments meet, because those routes carry matter inward over very long timescales. Norma appears to occupy one of these important junctions. One of the best known of the surrounding features is often called the Centaurus Wall. This is a broad chain or sheet of galaxies and galaxy systems that extends across a large part of the nearby sky and includes important concentrations linked with the Centaurus region. The word wall can sound more solid than it truly is, but the scientific meaning is simple. It refers to a long, connected overdensity of galaxies, not to a hard barrier. In the Great Attractor direction, this wall-like structure provides one major route along which matter is arranged. It helps explain why the region has influence that spreads beyond the immediate boundary of one cluster. The pull does not arise from a single lump alone. It emerges from an extended landscape of excess mass. Another important component is the structure often described as the Norma Wall, or the broader supercluster-like feature passing through the Norma region. This is not entirely separate from the surrounding network. It is another way of describing the long connected distribution of galaxies that crosses the hidden sector near the cluster. Observations in optical, infrared, and radio wavelengths have gradually revealed that galaxies continue across the obscured zone in coherent patterns. These patterns resemble the large walls and filaments seen in clearer parts of the sky. Norma is therefore not just near a concentration, it is embedded within one, and likely at the intersection of more than one significant branch of the web. This intersection is scientifically important because it helps explain why the region carries such strong dynamical influence. A massive cluster at the crossing of two or more large-scale structures can gather matter from several directions. Over billions of years, those inflows deepen the potential well and make the region more influential on surrounding galaxy motions. The cluster itself supplies a dense central node, but the connected walls and filaments broaden the volume over which mass is distributed. The result is a structure of many parts acting together. The surrounding flow field then reflects not only the pull of the core cluster, but also the shape of the larger network feeding into it. This also clarifies why the Great Attractor has often resisted simple description. If the region were one isolated, round, compact concentration, the surrounding motions might point to it in a more direct and easily summarized way. Instead, the mass is spread across clusters, galaxy-rich walls, and filamentary bridges. Some galaxies drift toward Norma along one structural path. Others are influenced by neighboring concentrations connected through the same web. The gravitational field becomes the combined effect of several linked features. A broad convergent zone naturally results from such an arrangement. The Great Attractor is therefore not mysterious because gravity behaves oddly there. It is mysterious because the relevant mass is extended, partially hidden, and arranged in connected forms rather than in one tidy object. The geometry of this region also matters observationally. When a wall stretches across the sky, especially near the zone of avoidance, it can be difficult to trace continuously. One segment may be clear in one survey, another may appear mainly in infrared data, and another may emerge more strongly through hydrogen observations in radio wavelengths. Yet when these datasets are compared, they suggest that the structures join into larger coherent patterns. the picture that emerges is not of isolated clusters scattered by chance, but of a web segment with real continuity. This continuity is one reason the Great Attractor region can influence motion across such a wide surrounding volume. Dark matter is a silent part of this connected system. The galaxies mark the structure visibly, but they do not contain most of the total mass. The walls and filaments almost certainly include dark matter spread along the same large-scale routes. In current cosmology, visible galaxies form within deeper halos and strands of dark matter. This means that a wall of galaxies is also a sign of a wall-like concentration of total mass, and a filament of galaxies traces a filament of deeper gravitational substance. The mass responsible for the regional flow is therefore larger than the luminous pattern alone would suggest. Light outlines the web. Gravity belongs to the fuller structure underneath. In this region, the Great Attractor becomes easier to picture in accurate terms. It is not a single unseen monster hidden behind the Milky Way. It is a densely structured part of the nearby cosmic web, with Norma as a major central node and with connected walls and filaments extending around it. The region behaves like a gathering point because matter has been funneled there along these large routes over immense spans of time. The attraction is broad because the structure is broad. The mass is not concentrated only at one point. It is distributed across an interlinked environment. This understanding brings calm to the problem. The extraordinary motions of galaxies in the surrounding region do not require an extraordinary kind of physics. They require a realistic map of ordinary gravity acting through a complicated large-scale structure. Norma matters, Centaurus matters, the connected walls matter, the filaments between them matter. Together they create a regional concentration strong enough to guide the flows of galaxies over large distances. The inward heart of the Great Attractor is therefore not one body in isolation, but a web junction of clusters, walls, and filaments whose combined mass gives the region its power. To understand how strongly a region of the nearby universe pulls on surrounding galaxies, astronomers do not begin by measuring force directly in the ordinary everyday sense. They begin with light, distance, and motion. From these, they build an indirect map of mass. The method is patient and layered. A galaxy is observed on the sky. Its spectrum is measured. Its redshift is found, meaning the amount by which its light is stretched toward longer wavelengths. That redshift gives the first estimate of how fast the galaxy recedes as part of the general expansion of the universe. But redshift alone does not reveal the full gravitational story. To learn whether a galaxy also carries an extra drift caused by surrounding mass, astronomers must know how far away it truly is. Distance is the difficult part. In astronomy, distance cannot usually be taken from redshift itself when the goal is to study local flows, because redshift includes both cosmic expansion and any extra motion along the line of sight. A separate distance estimate is therefore needed. This is done with distance indicators, objects or galaxy properties whose true brightness or true scale can be inferred well enough that their observed appearance reveals how far away they are. A Cepheid variable star, for example, changes brightness in a regular way, and the period of that change relates to its true luminosity. A Type 1. A supernova reaches a known range of peak brightness after correction, so its apparent brightness gives distance. Spiral galaxies also follow useful relations between their rotation and their luminosity, allowing their intrinsic scale to be estimated statistically. In large, smooth galaxies, tiny variations in surface brightness can also be used as a distance clue. Each method has limitations, but together they form a distance ladder reaching outward through the nearby universe. Once astronomers have both a redshift and an independent distance, they can compare the observed recession with the recession expected from expansion alone. If a galaxy appears to recede faster than expected, slower than expected, or even slightly toward the observer compared with the average background, then the difference indicates an extra motion. That extra motion is the peculiar velocity. It is the most direct sign that the surrounding mass distribution is uneven. A galaxy drifting toward a dense region will have part of its motion added to or subtracted from the expansion, depending on the viewing direction. One measurement by itself is only a small clue. Thousands of such measurements begin to reveal the shape of the flow field. This work depends on precision, because the signal is subtle. Distance indicators are never exact. Dust can dim light. Stellar populations can vary. Galaxies are not perfectly standard candles or perfectly standard rulers. Supernovae are powerful tools, yet they are rare and must be calibrated carefully. Relations based on galaxy rotation or internal structure carry scatter. Even the observed redshift must be corrected for the motion of Earth around the Sun, the Sun's motion within the Milky Way, and the Milky Way's motion inside the local group. Each correction is small compared with the full scale of the universe, but each matters when the goal is to detect motions of a few hundred kilometers per second within the nearby cosmic flow. Because individual measurements are noisy, astronomers rely on numbers and patterns rather than on one dramatic example. A large catalogue of galaxies with measured distances and redshifts makes it possible to infer a regional velocity field. The galaxies are not simply plotted as isolated arrows. Their motions are combined statistically and smoothed, so that the broad common drift becomes visible through the noise of individual errors and local orbital motions. This smoothing must be done with care. Too little smoothing leaves the map cluttered with random scatter. Too much smoothing erases genuine structure. The craft lies in preserving the large flow without pretending to know more detail than the data can support. From this reconstructed velocity field, astronomers can go one step further. Gravity links the distribution of mass with the pattern of motion. If galaxies stream inward through one region and diverge from another, then the underlying density field is not uniform. Mathematical methods allow the observed flow to be translated into an estimate of where matter is concentrated and where it is deficient. The result is not a photograph of hidden mass. It is a reconstruction, a best physical description of the density landscape most consistent with the measured motions. In this way, astronomers move from light to redshift, from redshift to distance, from distance to peculiar velocity, and from peculiar velocity to the underlying mass field. Redshift surveys provide another essential part of the method. Even when a galaxy has no independent distance measurement, its redshift still helps place it within the broad three-dimensional structure of the nearby universe. Large surveys reveal clusters, walls, and filaments by mapping where galaxies gather. This visible structure can then be compared with the reconstructed velocity field. If the motions point toward regions where redshift surveys also show an excess of galaxies, confidence grows that the interpretation is physically sound. If motions suggest hidden mass where optical surveys are incomplete, then astronomers turn to infrared, radio, or X-ray observations to search for the missing structures behind dust and stellar crowding. The different methods support one another. A flow map suggests where the pull lies. A sky survey helps identify what visible structures trace that pull. In regions like the Great Attractor, this combination becomes especially important. The Milky Way obscures direct optical views across part of the critical sky, so no single technique can solve the problem alone. Distance indicators reveal the unusual galaxy motions. Redshift surveys map the clearer parts of the surrounding structure. Infrared and radio work recover galaxies hidden behind dust. X-ray observations reveal hot gas in rich clusters. Together they provide multiple ways to approach the same mass concentration from different angles. The final picture remains a reconstruction, but it is anchored in many independent observations that point in a consistent direction. There is an important discipline in this method. Astronomers do not claim to see gravity itself. They infer gravity from the way light-bearing objects move through space. They also do not assume that visible galaxies contain all the necessary mass. When the motions are stronger than the luminous matter alone would allow, dark matter becomes part of the explanation. The map of pull is therefore a map of total mass, not merely starlight. This is why flow studies are so powerful. They turn motion into evidence for the unseen. At this inward stage, the Great Attractor becomes measurable not by direct grasp but by accumulated inference. Light provides redshift. Distance indicators separate background expansion from extra drift. Many galaxy motions combine into a flow field. That flow field is translated into a density map. The strength of attraction is then read not from one object in isolation, but from the coordinated behavior of galaxies across a wide region. This is how astronomers measure pull in the nearby universe, by turning patient observations of light and distance into a gravitational geography of mass. By the time the inward path reaches the mass budget of the Great Attractor region, a simple question becomes unavoidable. Is the visible light enough to explain the observed pull? The quiet answer from modern astronomy is no. The galaxies that can be seen in clusters, walls, and filaments trace an important part of the structure, but they do not supply enough mass by themselves to account for the full strength of the motions observed across the nearby universe. The same conclusion appears not only in this region, but across cosmology as a whole. Visible stars are only a fraction of the matter that gravity requires. The larger share belongs to matter that does not emit light in any ordinary way. This unseen component is called dark matter. The term dark matter can sound more mysterious than it needs to be. It does not mean that the matter is black like soot or shadow in any familiar visual sense. It means that it does not shine, glow, or absorb light in the simple ways that stars, dust, and gas do. Its presence is inferred through gravity. Galaxies rotate too quickly for their visible stars alone to hold them together. Galaxy clusters contain too much motion and too much hot gas to be bound by luminous matter alone. Larger structures in the cosmic web grow in ways that fit a universe, containing a great deal of additional unseen mass. In each case, light outlines the structure, but gravity reveals that more mass is present than the eye can count. The Great Attractor region follows this same rule. Clusters such as Norma contain many visible galaxies, and those galaxies are undeniably massive. Each one holds stars, gas, dust, stellar remnants, and dark objects such as black holes and neutron stars. Yet when astronomers estimate the total mass needed to account for the cluster dynamics, the hot gas between galaxies, and the broader regional flow of surrounding systems, the visible stellar matter falls well short. Even the hot intracluster gas, which contributes a substantial amount of ordinary matter, does not close the gap. The gravitational pull implied by the motions points to a larger total mass than ordinary luminous material can provide. This is one reason the visible appearance of a region can be misleading. A rich cluster may seem impressive because of its many galaxies, but the galaxies themselves are only the bright markers of a deeper structure. Around every large galaxy sits a dark matter halo, an extended concentration of unseen mass that reaches far beyond the bright stellar disk or central bulge. A cluster then forms not merely from the sum of the galaxies as visible objects, but from the combination of their halos, the larger common halo of the cluster, the hot gas, and the diffuse matter spread through the environment. Walls and filaments also trace larger dark structures. A chain of galaxies seen across the sky usually marks a deeper filament of total mass. The full gravitational landscape is therefore larger and heavier than the luminous pattern alone suggests. This is especially important in the Great Attractor because the region is not one isolated object. It is an organized network of clusters, walls, and filaments. If the visible galaxies were all that existed, the pull would be more limited and the flow field would be weaker. Instead, observations indicate that the surrounding structures are embedded within a more extensive dark matter framework. The galaxies mark where matter has condensed enough to form stars, but the broader gravitational influence comes from the total distribution of mass, much of which remains unseen. In that sense, the visible region is like the lit surface of a deeper terrain. The light shows where the structure rises most clearly, while gravity responds to the full hidden volume. The hot gas inside galaxy clusters adds another layer of understanding. In clusters such as Norma, X-ray observations show large reservoirs of gas heated to extreme temperatures. This gas is ordinary matter, not dark matter, and it often outweighs the mass locked into the stars of the galaxies themselves. Even so, when the full cluster is studied, the gas plus stars still do not amount to enough mass to explain the depth of the gravitational well. The motions of galaxies inside the cluster and the temperature of the gas both point to a larger unseen component. This means that even ordinary matter beyond starlight is not enough. The missing mass problem remains, and dark matter provides the most widely accepted solution. The strength of this conclusion does not rest on one method alone. Galaxy rotation, cluster dynamics, gravitational lensing, the growth of structure in the early universe, and the pattern of the cosmic microwave background all support the presence of dark matter. Gravitational lensing is the bending of light by mass. When light from more distant galaxies passes near a cluster, the cluster's gravity bends the path of that light. By measuring the amount of bending, astronomers estimate the total mass present, not just the light-emitting matter. In rich structures, lensing repeatedly shows more mass than visible galaxies and hot gas can explain. The same general lesson applies in the Great Attractor region. The pull belongs to the total mass field, and that field is dominated to a large extent by matter that does not shine. This does not mean astronomers know exactly what dark matter is in the particle sense. Observations indicate that it behaves gravitationally, and that it moves slowly enough in the early universe to help build the web of galaxies now observed. It remains uncertain which microscopic particle or substance accounts for it. That uncertainty, however, does not weaken the practical conclusion for large-scale structure. Whatever dark matter is in detail, it acts as a major component of the mass budget. Without it, the Great Attractor region would not possess the same gravitational depth, and the surrounding galaxy flows would be harder to explain within the ordinary laws of gravity as they are currently applied in cosmology. The contrast between light and mass is therefore central to understanding attraction on these scales. A map of galaxies is real and valuable, but it is incomplete. It shows where stars have formed and where luminous systems gather. It does not by itself reveal the full extent of the mass that guides motion. The Great Attractor is a useful example because its fame first grows from the motion of galaxies, rather than from a spectacular optical object. That fact already hints that visible light is not telling the whole story. The regional pull is stronger and broader than the eye alone would predict, because the true structure includes a large dark component wrapped around and between the visible systems. In this region of the script, the inward view settles on the simple truth that missing light does not mean missing mass. The Great Attractor pulls not because it shines with exceptional brilliance, but because it contains a large concentration of total matter, much of it dark, visible galaxies, hot gas, cluster cores, and walls of stars all matter. Yet they are only the luminous face of a deeper gravitational framework. The motion of galaxies across the nearby universe makes that framework visible in effect, even where it remains invisible in light. The pull is therefore not carried by stars alone. It belongs to a larger hidden mass that gives the Great Attractor region much of its quiet strength. As measurements improve and maps of the nearby universe grow more complete, the idea of the Great Attractor becomes more refined. The earlier picture is simple and powerful. Galaxies, including the local group, show an extra drift toward one broad region of sky. A hidden mass concentration seems to lie there. The Norma cluster and its connected structures give that concentration a real and substantial center. Yet the more carefully astronomers reconstruct the surrounding flow, the more they find that the motion cannot always be assigned to one single nearby source acting alone. The Great Attractor remains an important part of the story, but the story itself becomes wider and more layered than the earliest version suggested. This refinement is not a sign that the original idea fails. It is a sign that the nearby universe is more connected than a first description can capture. A large-scale flow may point toward one dominant region without ending there in a complete sense. Galaxies respond to the whole gravitational landscape around them. If one mass concentration lies nearer and another, even larger one lies farther along a related direction, then the resulting motion can reflect both. The path of flow may converge first toward a nearer basin and yet still be shaped by deeper structure beyond it. This is one of the main lessons of later work on the Great Attractor region. A major part of this revision concerns the Shapley concentration, one of the richest known supercluster regions in the nearby universe. Shapley lies farther away than the classical Great Attractor region, yet it contains an extraordinary amount of mass spread across many clusters and connected structures. Because of that mass, it exerts influence over a very large surrounding volume. When astronomers compare observed galaxy flows with reconstructed density fields, Shapley appears increasingly important as a contributor to the motion of galaxies on scales larger than the immediate Norma-centered region. In simpler terms, the nearby flow may be drawn partly by the Great Attractor region in front, and partly by the even greater mass farther beyond. This changes the old picture from one of a single hidden destination to one of nested gravitational influence. A galaxy group may drift toward the Great Attractor sector because the nearer mass there is real and strong. At the same time, the larger regional flow feeding into that sector may be enhanced by the pull of Shapley farther inward along the broader landscape. The motion field then becomes a linked sequence rather than a single isolated plunge. The Great Attractor remains meaningful, but it is no longer always treated as the final or sole answer to the local group's drift. It may instead be one major node inside a still larger current. Another refinement comes from the role of underdense regions, especially cosmic voids. A void is a broad region with relatively little matter. Such a region does not push galaxies in the ordinary mechanical sense. Gravity still acts only through mass. Yet when one side of a galaxy's environment is unusually empty, the pull from denser regions on the opposite side becomes comparatively more effective. In a reconstructed flow map, this can make galaxies appear to stream away from the emptier region and toward richer structures. The effect is sometimes described in a way that sounds like repulsion, but the physical meaning is more careful. Matter moves toward where gravity is stronger because there is less competing mass in the other direction. This is important for the Great Attractor because the local group and its neighbors do not live in a balanced setting. Nearby voids help shape the path of flow just as rich clusters do. Motion in the local universe is therefore not determined only by what lies ahead in the direction of greater mass. It is also affected by what is missing behind or to the side. A basin of attraction forms within a contrast field. Dense regions gather motion, while emptier regions leave fewer competing pulls. The observed drift of galaxies can thus reflect both attraction toward mass concentrations and the influence of surrounding underdense territory. With these refinements, the Great Attractor becomes less like a single answer and more like a key part of a regional system. Norma and its network still matter greatly. The Hydra Centaurus foreground still matters. The walls and filaments crossing the obscured sky still matter, but farther structures such as Shapley and neighboring voids in the local cosmic environment also participate in shaping the final flow. The local group's motion is therefore best understood as the result of a combined gravitational geography, rather than the effect of one isolated object hidden behind the Milky Way. This broader picture also helps explain why different studies have sometimes emphasized different centers of influence. Much depends on the scale of the survey, the set of galaxy distances available, the method of reconstruction, and the depth to which the flow is traced. A study focused on nearer peculiar velocities may highlight the Great Attractor region strongly. A study extending farther into the surrounding large-scale structure may find a greater contribution from Shapley or from the balance between dense and underdense regions. These results need not contradict one another. They may simply be describing different layers of the same connected landscape. The revised view brings the Great Attractor closer to the ordinary logic of modern cosmology. The cosmic web is built from many interacting structures, not from one dominant node controlling everything nearby. Galaxy motions emerge from the sum of these structures across a wide volume. Some are visible as rich clusters. Some are traced mainly through large walls and filaments. Some are inferred from the comparative emptiness of voids. The Great Attractor keeps its significance because it names a real and powerful convergence region. What changes is the recognition that the surrounding motion field does not belong to that region alone. In this part of the inward path, the mystery becomes more accurate rather than less compelling. The Great Attractor is not undone by revision. It is placed into a fuller setting, where its influence can be weighed against other major structures. The nearby universe appears less like a scene organized around one hidden mass, and more like a connected gravitational terrain with several large contributors. The flow toward the Great Attractor remains real. The mass around Norma remains central. Yet observations indicate that the broader drift of galaxies also carries the imprint of deeper concentrations farther along the web and of emptier regions nearby that leave the pull uneven. The revised picture is therefore quieter, broader, and more faithful to the structure of the local universe. At the deepest inward point of the present scientific picture, the Great Attractor is no longer treated as a single hidden object waiting to be uncovered in full light. It is better understood as a complex gravitational region inside the nearby cosmic web, one that gathers together several lines of evidence without reducing them to one simple body. The name remains useful because it describes a real convergence in galaxy motion. Yet the modern meaning of that name is more careful than the older popular image. It points to a broad inner landscape of mass, flow, and partial concealment, not to one isolated cosmic engine pulling everything around it in a direct and simple way. This is the quiet center of the mystery. The Great Attractor exists as a meaningful feature in the motion of galaxies. The local group and many other systems show that the nearby universe is not moving in a perfectly even way. Flow reconstructions reveal a broad inward tendency. The Norma cluster stands as a major concentration in the right hidden sector. Connected walls and filaments give that sector a larger structure. Dark matter provides the extra mass needed beyond visible light. Farther structures, such as the Shapley concentration, appear to deepen or extend the wider flow. Nearby voids help shape the contrast field through which galaxies move. None of these elements cancel the others. Together they form the present understanding. The Great Attractor is the name for an inner region where these influences meet most strongly in the local dynamical map. This means the mystery has changed form. In earlier language, the question often sounds like a search for the thing pulling galaxies. In current language, the better question concerns how a connected mass distribution produces the observed flow, and how that flow should be divided among several nested structures. The emphasis shifts from one object to one landscape. A galaxy does not respond to a label. It responds to the full surrounding gravitational field. That field can contain a dense nearby node, extended walls of matter, connected filaments, larger concentrations beyond, and under-dense regions that alter the balance of pull. The inner meaning of the Great Attractor is therefore not a single answer, but a structured region within a wider network of causes. This more careful picture also changes how certainty is described. Some parts are well established. Observations indicate that the local group has a substantial motion relative to the cosmic microwave background. Observations indicate that galaxy peculiar velocities across a large surrounding volume are not random but show coherent flow. Observations indicate that the Norma region contains a massive cluster and associated structure near the hidden heart of the classical Great Attractor direction. Observations indicate that visible galaxies alone do not provide enough mass, and that dark matter must dominate much of the gravitational field. These points belong to the stable framework of the modern account. Other parts remain less final. It remains uncertain exactly how the boundaries of the relevant basin should be drawn in every direction. It remains uncertain how much of the local group's motion should be assigned to the nearer Great Attractor region, as distinct from the pull of deeper structures such as Shapley. It remains uncertain in full detail how all the obscured filaments and walls crossing the zone of avoidance connect into one continuous map. These are not weaknesses in the basic science. They are the normal uncertainties of a difficult observational problem. The Milky Way still blocks part of the view. Distance measurements still carry scatter. Flow reconstructions still depend on statistical methods and incomplete sampling. The inner mystery survives not because astronomy lacks a framework, but because the framework describes a rich and partly hidden reality. There is something fitting in this. Gravity itself is simple in principle, yet its large-scale expression in the nearby universe becomes intricate because matter is arranged in intricate ways. The Great Attractor is one of the clearest examples of that truth. It shows how a region can be famous not because it shines more brightly than all others, but because the motion of galaxies reveals a depth of mass and structure that ordinary sight alone does not capture. The region becomes known through effect before it becomes fully known through appearance. In that sense, the Great Attractor remains one of the more elegant lessons in cosmology. The universe can disclose its hidden architecture through slow collective drift. The present view is therefore neither a full solution nor a return to confusion. It is a mature middle state. The basic phenomenon is secure. The Milky Way's neighbourhood moves within a larger flow. The classical Great Attractor region near Norma is a real concentration within that flow. The wider surrounding structures matter as well. The best scientific picture does not flatten these facts into one phrase, yet it does not abandon the phrase either. Instead, it uses the name with precision. The Great Attractor is a historically rooted and still meaningful description of the inner convergence region in the local gravitational landscape. Even though the true landscape is broader than the name once implied, seen from this deepest region, the nearby universe appears calm, structured, and unfinished in the best scientific sense. It is calm because nothing here requires exotic violence or sudden cosmic drama. Ordinary gravity, acting over immense spans of time, is enough. It is structured because galaxy flows, clusters, walls, and voids fit together into a coherent web. It is unfinished because every improved survey, every better distance catalogue, and every clearer view through the obscured sky can refine the map further. The mystery remains open at the edges, but not empty at the centre. Much is already known. The remaining uncertainty has shape. So the Great Attractor in its innermost present meaning is not one hidden monster beyond the Milky Way. It is a deep convergence region inside the local cosmic web, anchored by real mass concentrations, enriched by dark matter, broadened by connected structures, and interpreted through the measured motion of galaxies. It is both a place and a pattern, both a historical idea and a modern reconstruction. Its exact reach and full hierarchy remain under study, but its role in the motion of the nearby universe is not imaginary. The galaxies drift, the flow field converges, and the mass landscape of the local cosmos continues to reveal itself with patient clarity. In that slow revelation, the Great Attractor remains what it has become in modern astronomy, not a simple answer, but a precisely framed mystery at the inward heart of our moving neighbourhood. The nearby universe settles into a quieter shape when the motion is allowed to speak for itself. Galaxies do not drift through a featureless emptiness. They move through a landscape built over immense spans of time, where matter gathers into clusters, stretches into filaments, spreads into walls, and thins into wide voids. Within that landscape, the Milky Way is not still. The local group is not still. Both belong to a slow current flowing through a larger gravitational terrain. The Great Attractor remains part of that terrain, not as a single dramatic object, but as a deep inner region where the surrounding flow converges. Norma stands there as one heavy landmark. Hidden structures continue across the obscured sky. Dark matter deepens the unseen framework. Farther concentrations and nearby emptier regions both help shape the path of motion. The picture is large, connected, and patient. From Earth, inside the dusty disk of the Milky Way, the view outward is never complete. Yet even through that partial view, a calm order emerges. Light reveals galaxies. Distance reveals drift. Drift reveals mass. Step by step, the nearby cosmos becomes less mysterious in one sense and more beautiful in another. What first seems like a single hidden pull becomes a whole geography of movement. In the end, the Great Attractor is not only a destination in space, It is also a reminder that the universe can be understood by following quiet patterns over vast distances. A small difference in galaxy motion, measured with care, can uncover the shape of a region too broad to hold in ordinary thought. The local cosmos continues to expand, and within that expansion, its structures continue their slow influence, guiding galaxies along paths laid down by gravity and time.